Investigating exponential relationships. So what we're going to start with is first and second differences, okay? And this is just a recap from grade 9 and grade 10, and then we're going to graph the relation, okay? So for first differences, what we're going to do is we're going to start at the bottom of the y's, and we're going to subtract. 8 minus 6, that's 2. 6 minus 4, well, that's 2. 4 minus 2, well, that's 2. Okay, and if we keep going up, we're going to see that the first differences are all 2. Oh, will be 1 box less. Okay, and then of course for the second differences will be 2 boxes less because this top number doesn't have anything to subtract. Okay, so as soon as we see that the first differences are constant, we can stop. Because essentially the second difference is 2 minus 2, all of these are going to be 0. So that doesn't help us at all. Okay, so first differences are constant. Therefore, since the first differences are constant, the relation is linear. And we know that from grade 9. So if we were to, I'm going to move this down as much as I can. Okay, negative 3, 1, 2, 3, 1, 2, 3, 4. Negative 2, negative 2. Negative 1, 0. 0, 2. Okay, if we were to graph this, 1, 4. Okay, this is what it will look like, and then that will be up there. Okay, so this is clearly a line. And if you look at the first 4 letters in linear, okay, they spell out line. So if the first differences are constant, it's a line. Okay, now this is example 2. Let's take a look at the first and second differences of this one. Okay, so let's do from the bottom to the top, 9 minus 4. And that equals 5. Let's go 4 minus 1. That equals 3. 1 minus 0. That equals 1. 0 minus 1, that's negative 1. Okay, 1 minus 4, that's negative 3. 4 minus 9, that's negative 5. Okay, and this is just going to be boxed in. Okay, these are not constant. So let's find the second differences. Okay, let's go up the first differences. 5 minus 3 is 2. 3 minus 1 is 2. 1 minus negative 1 is 2. And if you keep going, you're going to get 2's. So therefore, since the second differences are constant, this relation is quadratic. Okay, so when we look at quadratic, we look at y equals x squared. This is the second difference. Second difference is going to be constant. If we looked at linear, and let's just box this in because this answer is not from here. Linear, y equals mx plus b. This x has the exponent of 1. 1 being the first differences are going to be constant. Okay, and if we were to graph this, no, that's wrong. 1, 2, 3, 4. Okay, it's going to look, oops, like this, just smoother, sorry. Okay, so y equals x squared. This is quadratic. Okay, let's take a look at the first and second differences of this relation. Okay, let's go 64 minus 32, I get 32. 32 minus 16, I get 16. 16 minus 8, I get 8. 8 minus 4, I get 4. 4 minus 2, I get 2. 2 minus 1, I get 1. Okay, these are clearly not constant. Now let's try again. 32 minus 16, I get 16. 16 minus 8, and you should be seeing a pattern here. Okay, 4 minus 2 is 2. 2 minus 1 is 1. Are these constant? No. Okay, since the first and second differences are not constant, this relation is not linear, and we know that is not quadratic. Okay, if we were to plot this, So and 2, negative 1 and 4, 0 and 8, 4, 5, 6, 7, it would be like actually up here. Okay, this is actually exponential. So let's actually add to this. Let's add to this and let's right over here, ratio. Okay, let's find the ratio between the y's. So I'll do it down here. I'm just going to rewrite the y column and then I'm going to write the ratios. Okay, so we have 1, 2, 4, 8, 16, 32, 64. So if we took 64 over 32, okay, that's a 2-to-1 ratio. 32 over 16, divide, that's 2. 16 over 8, that's 2, right? And if you actually took a look when we were writing out the numbers, you could have seen that all of them were doubled, okay? And 2 over 1, okay? So since the ratios are constant, therefore, since the ratios are constant, this is exponential. So if a question were to give you a table of values and say, is this exponential or not, what you're trying to do is you're looking for either the first or second differences, okay? If not, you're looking for the ratios. So here are a couple definitions, okay? So we're going to take a look at exponential growth, and this is nonlinear growth represented by its, of course, exponential, and this has an upwards curve. So this curve is going to look like it's going up. Okay, and exponential decay, again, nonlinear growth, it's represented by an exponential relation, but this one's going to be a downwards curve. Okay, and an asymptote is a line that a curve continually approaches but never actually touches or meets. Okay, so let's look at these graphs. So this graph, this blue graph right here, this is an exponential equation or exponential relation. And what happens is it approaches this y equals 0 as the horizontal asymptote. Okay, and it gets closer and closer to the horizontal asymptote but never actually touches it. Okay, and the bigger x climbs, the bigger x gets, the faster it climbs. Okay, so it's not linear, it's not climbing at the same rate. Okay, the bigger these x's get, the faster it increases. Okay, so exponential growth, again, going up, and exponential decay is coming down. Increasing versus decreasing. Okay, so let's determine if each relation is exponential, and you can go ahead and try these and then just check your answer. So I would first just see if there's a pattern. So actually, just a recap, all the x's have to go up by the same number. So 1, 2, 3, 4, 5, 6. Well, the x's are increasing by 1. So delta x is 1. So that's okay. We can use first differences or second differences or ratios. So, so this one's just asking us to determine if each relation is exponential. So we actually don't even care about like the first and second differences. Oh, here we go. First and second differences. We just care about the ratios. So let's go. 12 divided by 10. 10 divided by 8. 8 divided by 6. 6 divided by 4. 4 divided by 2. Well, that's obviously 2. Okay. And then 6 divided by 4. This is 1.5. And you can do this the entire way down. 8 divided by 6 is 1 1/3. Okay, but as soon as they're not constant, I don't even care. They're not exponential. Okay, let's try this. 729 divided by 243. 243 divided by 81. 81 divided by 27. 27 divided by 9. 9 divided by 3. each one of these is actually 3. So is this exponential? Yes. Okay, and let's try this one. 1296 divided by 625. 625 divided by 256. 256 divided by 81. 81 divided by 16. And then 16 divided by 1. Well, I'm going to start with 16 divided by 1 because that's just so easy. And then let's go 81 divided by 16. I get 5.0625. You know what? Let's just check one more. And I always do this just in case I made a little error. No, this one's 3.106, 160. And so on. So this one is not exponential. Got a little messy here, but that's okay. Okay, and number 2, which of the followings could represent exponential? A, no, this is linear. B, yes, it's increasing, right? It's growth. C, no, this is quadratic. And D, yes, this is exponential decay. Okay, example 3. A car purchased for $38,000 depreciates by 30% each year. So after a year, all that's left is 70% of the original value. Okay, and the relation's given to us, so this is going to make it so easy. V is the value of the car after T years. So let's find the value of the car after each period. Well, V equals 38,000 times 0.70 to the 1 year. Let's calculate that. Let's calculate 3 years. 0.703. Okay, let's calculate 5 years. And I would write all of these down first, because then I only have to pick up my calculator once. And my calculator holds, oops, this is 5. What was I thinking? My calculator holds the equation, so it's really easy to just override the exponent. So after 1 year, only 26,600, that's all your car's worth. After 3 years, oh my goodness, 13,034. It's not a lot of money, right? You can put a money sign on there if you'd like, okay? Or you can do that in the therefore statement, okay? So 6386.66. And 9 years, we have 1533.44.